and start off with Cryptography Fundamentals. And these are going to be what actually create those accounting guarantees that we saw last week. They're going to be what really turns that double entry book into a triple entry ledger based on cryptographic proofs. So, show of hands, who here has heard of SHA256, SHA hash function? Most of the room. Okay, so everyone's pretty familiar. That's good. That's great. We can go kind of quick through this. This is the first thing that comes up when you look up SHA. It just takes a lot of information on one side, and you have a little fingerprint on the other side. And that's really cool. That's really foundational to almost everything that we're going to do. Now, it sounds like you guys are pretty familiar with SHA. So you have some input, and it creates this big hash for the output. Similarly, if you make a little change in that input, the output looks just drastically different. And that is really cool. It's hard to do. And SHA is really neat because you can just take completely arbitrary information, like say this picture of a cat, and represent it in this hash function. And if you change even the slightest thing about this cat or this legal contract or anything, as sounds like you're kind of familiar, it completely changes this hash function. So it sounds like we're all kind of on a similar page here. I'm going to go a little quick through it. Just a little preface. So this is my first book. This is the manuscript of the book. It's got 100,000 words. It's on trading, finance. I took the entire manuscript, ran SHA on it, and got this hash on it. And what's cool is that this hash, for no matter what you put into SHA, reveals absolutely nothing about the input. This hash right here reveals absolutely nothing about the manuscript of the book. It reveals nothing about your inputs. And the only way to ever replicate this hash is to put the entire manuscript of this book into it. The only way to ever replicate this hash for the cat picture is for as far as we know, is to basically do the entire hash, is to have this cat picture or brute force every single cat picture that ever exists to get that same hash. And that is just computationally infeasible, and we're going to see how to implement in a second. But one thing I'm going to go over this real quick because it sounds like we're familiar, but one of my most favorite things in the whole world to do is to mess with just playing around with SHA. It's really cool understanding how much you can mess with it and how that leads into the security that you can implement with these hashes. So, anybody shout out your favorite color? Someone shout out favorite color.
Red.
Red. Okay, cool. So we type in red, and you just get this. I mean, you can't. So pretend red's not here. You have no way. It's just there's nothing. It's just this hash. And if you make any minor changes, you can see as I'm just typing in letters, it completely changes everything about that hash. And that is critical to the security of all the crypto systems. Effectively, every crypto system is based, every blockchain, every consensus mechanism, everything we're going to cover from this point forward is based on this idea of hash functions that you just don't get any information from. If you have this right here, and the cool thing we can do is we can copy this and we can paste it. Now we can find the hash of the hash. And you get absolutely nothing about the pre-image from the hash output of the function. And that is crucial, that is critical, because it allows you to do some really cool things. So, now that we have that kind of basis down, this is just SHA. You gotta understand, guys, just math, all right? This is just a bunch of complicated math. This is how you do SHA. It's like this is a coding implementation of SHA. SHA256, which is kind of the most popular one. All it is math, okay? And you can go and you can read through all the math on it. And the cool thing about SHA is that it's completely open. So everyone knows what the protocol is. Everyone knows how SHA works. And people have been trying to break SHA for decades. They just can't do it. And the most important factor of SHA256, and we'll see higher levels of security, but just as a baseline here with SHA256, is it gives you 2 to the power of 256 possible hash outputs, right? So you have 2 to the power 256 bit outputs. So it's a very large number, 115 quadrillion. It's a very, very, very large number. And this number right here is the basis for almost every piece of security that we have starting on the blockchain. It's really important to understand what this 2 to the 256 means, because the implications that it has for all of our security and all of the guarantees that we can make comes from this idea of the power of 256-bit security.
Now, this is a number so far removed from anything that we ever deal with that it can be hard to appreciate its size. But let's give it a try. 2 to the 256 is the same as 2 to the 32 multiplied by itself 8 times. Now, what's nice about that split is that 2 to the 32 is 4 billion, which is at least a number we can think about, right? It's the kind of thing you might see in a headline. So all we need to do is appreciate what multiplying 4 billion times itself 8 successive times really feels like. As many of you know, the GPU on your computer can let you run a whole bunch of computations in parallel incredibly quickly. So if you were to specially program a GPU to run a cryptographic hash function over and over, a really good one might be able to do a little less than 1 billion hashes per second. And let's say that you just take a bunch of those and cram your computer full of extra GPUs so that your computer can run 4 billion hashes per second. So the first 4 billion here is going to represent the number of hashes per second per computer. Now, picture 4 billion of these GPU-packed computers. For comparison, even though Google does not at all make their number of servers public, estimates have it somewhere in the single-digit millions. In reality, most of those servers are going to be much less powerful than our imagined GPU-packed machine. But let's say that Google replaced all of its millions of servers with a machine like this, then 4 billion machines would mean about 1,000 copies of this souped-up Google. Let's call that 1 kilogoogle worth of computing power. There's about 7.3 billion people on Earth. So next, imagine giving a little over half of every individual on Earth their own personal kilogoogle. Now, imagine 4 billion copies of this Earth. For comparison, the Milky Way has somewhere between 100 and 400 billion stars. We don't really know, but the estimates tend to be in that range. So this would be akin to a full 1% of every star in the galaxy having a copy of Earth, where half the people on that Earth have their own personal kilogoogle. Next, try to imagine 4 billion copies of the Milky Way. And we're going to call this your gigagalactic supercomputer, running about 2 to the 160 guesses every second. Now, 4 billion seconds, that's about 126.8 years. 4 billion of those, well, that's 507 billion years, which is about 37 times the age of the universe. So even if you were to have your GPU-packed kilogoogle per person multiplanetary gigagalactic computer guessing numbers for 37 times the age of the universe, it would still only have a 1 in 4 billion chance of finding the correct guess.
And that's the key. That's
By the way,
what really
this thing
allows
with
us
Bitcoin hashing
to
these
make.
days is that
Okay. That's what allows us. To make these hash functions the basis of almost everything that we do on the chain. Here's just an example block from just the Bitcoin blockchain as an example. And you can see this hash comes into play as the foundation for everything that the protocol is built on, with that idea that it is just, it's effectively none, that you're going to be able to just randomly guess what one of these are. It just doesn't, it's not going to happen. Okay, that's really important. We'll go back to that in just a second. Before that, anyone here ever scratched a CD? Okay. It's a sad story, right? But imagine a movie or a song or whatever. It was just one big long string on that CD, and you scratch it and it just ruins. The whole thing's broken. It never works again. That's not how it works, right? You scratch a CD, maybe there's a little glitch in the film or something, but it still works at the end of the day. That's because everything is kind of compartmented into little segments, and all the segments are strung together. And if you have a problem with one of the segments, you can just move along, move after it. There's some error correction you can do with movies. That's kind of the core principle. And now we're going to get into something that's related to that. It's extremely important for transaction validity. This is the basis of almost every single crypto system. Almost every blockchain uses a scheme extremely similar to this. And it's the idea of Merkle trees. So say we have some transaction between Charlie and David, and that transaction is just a simple message. You have a protocol that specifies the linguistics, but just say I pay Charlie $100 or David pays Charlie $100, vice versa, and you just have that block of text. And then what you do is you have a signature, which we'll get to in just a moment, and you take the hash of that transaction. So you get all the data in the transaction. Usually it's a lot more data than just who it is. There's a little bit more information. Maybe, I want to send them not just dollars, I want to send them some yen, however much you want to send them. You get all the information that you need for your transaction. And you take the hash of that transaction. So now, instead of storing like 20 lines of data for the transaction, instead of having all that information out there on the chain, you just take the hash of it, and as you saw earlier, it's just this little 128-bit string. And so when you just the hash of it, now what you can do is really cool. So as we saw earlier, when you take the hash of hello is always the same. When you take the hash of 100,000 word manuscript, the hash is always the same. It's deterministic, right? What you put in 10, you always will get the same hash out, based on the same premium. So with these hashes, what you can do is you take the hash of one transaction and then concatenate it. So you just have one transaction's hash and then another transaction's hash. You just put them together and you just hash them both and you figure out what the hash of the combined hashes are. And what's cool is all the modern cryptographic schemes allow you to do this, and it works really, really well. And so you combine these hashes to form this hash here. And then you combine all these hashes for the transactions to form this hash here. Does that make sense? Are we all kind of on the same page with how that concatenation, how that combination worked? Okay, okay. And so that works up to the Merkle root, basically just the top hash of all of the transactions in one of those little blocks, right? So one of those little slivers of all the information that you're carrying. So everything comes together. And what's cool with this scheme and what it really allows you to do that you can't do with most data structures is that you just have this hash here is published to the blockchain, and everything else you can query, but it's not, it's not as data intensive, not as storage intensive. So you can just store this header. And then if you want to prove this transaction to David, all you do is you just have this hash here, and if you take the hash of that authentic transaction, you can combine it, form this hash, combine these, form this hash, combine these, and then this is the verification hash that you'll see on the blockchain. So in terms of what that looks like, here you can see this Merkle root, and this is the Merkle root of every single transaction in this block. And most blockchains follow a scheme very similar to this, where you have this one Merkle root that is the hash of the hash of the hash of the hash of all of that big tree of transactions. And this here is block 69, 96, 22. And then you just add the blocks. And we'll see that here. So say we have just a big list, and this is a lot, so it looks like a lot. We're going to go through it slowly. Say you just have some big list of all the assets that everybody owns in a company. What we're going to see is you just have these payments. So say you have this check, you write the check out to Jane, and you just take the hash of that with the signature on it, and we'll look at that signature in just a second. And then that hash is going to contain it's the hash of all the information in that transfer. It's the hash and all the check. So the transaction's going to have the date, the money, it can have a memo, all that information. And then you just hash that, and that hash gets combined with all the other checks, just like this, combined with all the other valid signature here, which we'll see in just a sec. You just combine all those, and then you make up this Merkle root, and that Merkle root gets included in the next block in the blockchain, and then kind of depending on the consensus mechanism, which we'll look at a little bit later in the series, that gets appended to the block, the next block, the next block, the next block. And every single block has a big kind of tree of transactions, just like this one, that at the end of the day is just hashed transactions that allow you to have authentic guarantees without any trusted central party. Does that make sense? That cool? All right, super. And this acts as that receipt in the triple entry accounting system. This is, instead of having an auditor, instead of having a bank that you query, you can just query the Merkle root and then get all the hashes of the transactions in it. And then if you want to verify your transaction, all you have to do is get down to your transaction hash and just put in the information that you have for the transaction. Say I send you $100 and some other information. And if the transaction for I send you $100 matches the transaction that's on the blockchain that everyone agrees to, then you're valid, you're good. If you want to lie and say I send you $1,000, remember any little change that we make in the hash, in the pre-image, any little change that we make going into the hash function has a huge change on the hash function, and they just won't match. So that's how you would know that that would be invalid. And again, really important, the item you're comparing it to is on that public blockchain, that big floating tablet in the sky that has all of these receipts, which are, at the end of the day, just these Merkle headers, or something really very, very similar. Cool? Yes? Loving it? Okay, here's the best part. This is the part that Abraham talked a lot about last week, this idea of cryptographic signatures, because this is what everything falls down to. You can have the hashes, you can have the data structures all you want, but nothing matters if I can pretend to be Alice and just take all their money. It doesn't matter. These signatures are what allow it to happen. Now, traditionally, you have just the signature and it's, it's just ink, right? And you copy and paste, it's not the best thing. So we're going to look at here are cryptographic signatures. And these are based on the same principles of hash functions. That idea that it would take 4 billion times 4 billion times 4 billion, trillions of times the age of the universe to ever try to brute force alpha's public key. And at the same time, there's no way other. So basically, you have just a big random number that you input. And so this is what Abraham talked about last week, was some of the scandals around random number generators and how a lot of times they're not particularly secure. That was one of the kind of really big things he talked about with EC. That big EC conversation he had was all about the idea of a big random number generator. And so when you're generating your key, so let me show you guys sort of what this looks like in reality, so I can give you a tangible, I can actually do that. Oh gosh, here we go. So the idea with most of these signature schemes is that you generate a key once, and then that is your key forever. That becomes, everyone kind of here familiar with like your blockchain address, your Bitcoin address, where people send that money to. Okay, that's the public key. We'll come down to just a sec. But I really want to kind of crack down on this entropy, because this is really important in key generation, but it's also not particularly well understood a lot of the time. So this is just a generator function. It's just a program that allows you to generate cryptographic signatures just by following the exact same principles that we see right here. So all this is doing is very, very simple. It's taking in some random value. And a lot of times what the computer will do is generate this big random value all by itself. And for some use cases you can accept that, but usually you want to take this in, you want to generate your own randomness if you really want that next level of security. It isn't usually a huge deal elsewise if you just kind of do it for an individual level, just to show you how it works. So you have this big random number that comes in. It goes into the key generation function. So what that looks like, just like with SHA, just like with these hash functions, if you input one thing, you're always going to get the same output. It's deterministic. So if we input is our randomness 1, and we just force it to go to 12 words, we need 12 words. Yeah, so so if you put in 1 and you force to 12 words, you'll always get this 12-word phrase. This is the equivalent of what your secret information would be. This is the equivalent of what your secret key would be. This is this big red thing here, this big red private key. That's what we're looking to generate right now. It's the most important thing we're doing. So if you insert 1, right, we can get rid of it, we can put it back. You're always going to get the same signature. You're always going to get the same private key because it's all based on this entropy. And so the whole idea of generating a bunch of random numbers is that you make a secure enough generation function that you have a fairly secure privacy, and that becomes what you use to sign everything. And so usually what you'll do is you'll just use a random number generator like Abraham talked about last week, and you can just generate these all day. And what you'll see here is just a shortened version of that private key. And every single, is anyone here, are we familiar with key pairs, cryptographic key pairs? Not so much? Okay, we'll go a little more into that then. So this is where it starts to get really interesting. So every public key, every Bitcoin address, every blockchain address that you receive money or you send money if you're withdrawing from some exchange or you're getting a paycheck to your address or whatever, those are all public keys, right? And those public keys are all derived from just information, just that random private key. And so all you do is take the private key and you can just run, depends on the blockchain, depends on the protocol. But in general, all you do is just run some math functions on that private information, and and you'll get the seed. So here's kind of our seed. This would be the private information, and then here it is coded to 12 words so that it's easier to remember. And then if we scroll down, we can see all of these Bitcoin public keys, all these addresses that are generated using that private key. So these are just different private key paths that you can take to generate the addresses. You can generate as many as you want based on the private key. And the cool thing is that when you have any of these public keys, and we'll just keep it to 1 to be simple. Say you have this one public key, right? Say somebody sends Bitcoin to that one public key. the only person that can generate valid signatures for that public key is the person who owns this private key right here. And this private key has that same level of security, if not more in most cases with elliptic curves, that has that same level of security as the hash function. So it is just null. You can't just make up this number and then try to guess. It just doesn't happen, right? It's at the same level of security. And you can generate these all day long. These are 15-word mnemonics. And all they are, it's just information. And this information is the basis for the signature scheme. So in terms of what that looks like, you can do some pretty cool things. And I want to show it to you. So I just want to show you guys that for key generation. But now I want to show you what that looks like on an actual blockchain. So you can really see it happening. And one thing we're going to look at really important here is this idea of signing messages. So before, we were just computing the hash of a function. It was just a one way, right? Now what we're going to do is with these cryptographic key pairs that we've just generated, and we'll make some more, what we'll be able to do is sign a message, and then anybody can come in and verify that we used our secret to sign that message. And that's the basis for every single transaction on any blockchain. Everything comes down to this process, this verification right here. That's the basis for everything, and it has that security. So this is going to be kind of cool. We're going to do a little live test on the blockchain. So we're just going to create a key pair here. We got our public key and our secret key. And I'm going to go ahead and put this on test network. And we're going to, so all this did in the background here is it just did that random number process. And then with that random number, it generated a secret key. And with that secret key, it derived a public key. And so we can go ahead and just fund this on the test network. And what's cool is we can go ahead and actually explore. Stellar is pretty cool. It's kind of a fast block explorer or blockchain. Oh, please don't freeze. Okay, there we go. So we can actually go and see this account that we just created on the blockchain. And nobody can access it except us because we have this secret key right here that is linked to the account. So here we are pulling it up, and we can see we just, let's go over to the test network. This test network it's just like the normal blockchain, but it's a test network. There's some nuances behind it. It's not a huge deal. And so
it's designed to be valueless.
Thank you. Genius. Yeah, so we have 10,000 lumens here. In the real world, that's like $3,000, but since it's the test network, it's just like nothing. It doesn't matter. And we can see that with this function right here, we just had this account right here just sent us all that big money, basically. And so now what we can do, because we have this secret key and this public key, we can go over here and we can build a transaction. This transaction is just like any other transaction, like anywhere. So you can pick who you're sending money to. I'm going to paste in our source account, is the account we just generated. I'm going to pull up a sequence number here. It's just some fancy words. Don't worry about that. It's not a huge deal. And just like any other, we can just scroll down here and we can just select transfer, right? So we can send money to somebody. And the way we verify, so say we want to send money back to this guy that just gave us 10,000 lumens. When we're sending that money to him, all we put in is his public key, just like people paying us would pay, as this guy just did. They pay our public key, and you can see that you get that payment. It's just based on this public-private key cryptography. That's the basis for everything. And then here's the really cool part. So say we want to send him over 9,000 lumens. We go ahead and just code it in here. And this is kind of what the actual data in the transaction would look like. So we talked about the transaction data that gets hashed. Here's all the data going into the transaction, and there's a little bit more data going on behind the scenes. And all of that data gets hashed right here. You see this hash? That's the hash of the transaction data that we're going to see in just a minute. We're going to submit to the blockchain. So what we do now is, this is the critical part, because if we try to submit this right now, right? If we try to submit it right now, like nothing's going to happen. It's not going to work because there's no signature. You can see here we have all the data that we put in, but there's no signature, right? And so there's no authorization. It doesn't work. And that's the key, right? And if we put in just an arbitrary signature, it's not going to work, right? You have to have a valid signature. And so that's what we're going to do here. We're going to sign the transaction. If we try to just make something up, you can see you can't basically fake it, right? It's the same level of security that we saw with the hash functions, if not more. And so what I'll do is I'll copy our secret key, and this is just an incredibly large amount of information. You can't really get it anyway unless you actually are the account owner and you have the private key. So we put in our private key here, and voila, the transaction's signed. Here it is with the signature. And since we have this valid signature here, we go ahead and submit it to the blockchain, and there you have the hash, which is the same as the hash we saw before. Of course, it's got that signature appended to it. Yeah, what's up?
So if someone has access to your private key, they can have access to all your money?
Exactly, yeah, that's 100%. So that's why you keep it really secure. So usually how you'll do it, this is how we do it at the company, is you have like one main backup that's held in like a safe in an armed facility, something like that. And then it's usually in metal, so you'll kind of, so we looked at 12-word mnemonics. That's extremely common in the industry. So you'll just get metal plates a lot, and this is more for institutional grade. And this is like the high level of, you can also just write this on a piece of paper and hide it somewhere in your house. It doesn't have to be this complicated. But yeah, so you just want to ensure the security, and if you need backups of it, there's a couple of cool ways you can do that. There's some cool little strategies you can do where you have 4 secrets and you need 3 of them to access your account, stuff like that. It's all just math, right? Because it's just this big random number, and it's just figuring out how to store that number. And there are some really neat ways, like you can encode it into short phrases. So the signature, no, that's the really cool part. So the signature right here is only for this one transaction. This signature, basically, you take all of this information here, and this is really the magic of everything. You take all the entire message, and then you sign that specific message. So the signature is associated to your public key, the private public key pair, but it's only for that one message. So if you try to copy the signature that we just created on any other transaction, it's not going to work. Mostly, one of the reasons why is because we have this sequence number right here. You'll see, since we just submitted this transaction to the blockchain, you'll see in just a sec, you see this sequence number here. This is just one way you can do that. The sequence number here ends in 45, and if we go to make a new transaction, even if everything is the same, even if we're paying the same person, even if we're paying the same person the exact same amount of money, even if all the transaction information is the same, what you'll see is when we fetch the sequence number, it got incremented by 1. So if we're up by 1, we just had a transaction. And so that's one of the strategies so that you always have unique data that you're signing, and that signature is always linked directly to the data. So if we go through this whole process again, and we go and sign this in the transaction signer, and we put in our key, which is right here, we'll see that this signature right here, ending in 44, oh gosh, well, we'll see that this signature right here is completely different than the signature that we have over here, right? So this one is AQCA at the end, it's all a bunch of random number. And then here, this one ends in RW4. It's completely different. These signatures are just for the transaction. And also, you saw in that example, we only changed one number in the entire transaction, and it completely changed the hash signature. And so it has that same function as the hash signature, very unique and always only for that one. Yeah. The signature, it is kind of like a scheme you go through. This is using elliptic curve cryptography, so we talked about elliptic curves last week. It's similar to hash. You can kind of think of it similar, but there's a little bit of more math going on behind the scenes there. We'll look at actually some good resources on how to dive deeper into that at the end of the seminar. That'll be good. And so yeah, so we can refresh our account here. and we can see that that signature is valid, propagated to the network, and voila, we sent that money on the blockchain. How many people? I think it was only a couple of people the first week said they'd ever transferred assets on the blockchain before. Only a few people. Well, I think you guys can all say that you were at least an accomplice to a blockchain transaction because you have now transferred an asset, a worthless asset, on the blockchain, and that is basically the basis of everything that you'll do. That was done. Right. So that would be like one central party, that central double entry ledger, that central bookkeeping on an exchange versus here it's on the blockchain. Like when we submitted this, we used the Stellar Foundation website, but basically we submitted this to the entire Stellar blockchain. We didn't submit it to Stellar Corporation. There is no Stellar Corporation. And so that's the magic of everything that we'll see here with the blockchain, so the signature scheme is that you don't have that central point of failure, you don't have that central party, and instead you're relying on these cryptographic functions. And yeah. Same thing, yeah. Yeah, that's the basis. That's the cryptography behind the blockchain, and it's the basis for everything that we're going to see coming forward.